The dot product is the product of parallels. There are two examples that come to mind that use the dot product: power calculations and work calculations. Look at these two vectors, green vector A and orange vector B, with angle theta between them. Okay, let's figure out what the product of parallels is with vectors A and B, or in other words, what is vector A dot vector B? A dot B. If I project vector B onto vector A, I get this parallel projection. The component of vector B that's perpendicular to vector A is shown here. A parallel vector and a perpendicular vector always make a right angle. One more time, B subscript parallel is the parallel projection of vector B onto vector A, and B subscript perpendicular is the component of vector B that's perpendicular to vector A. Okay, this is a right angle triangle, so I can say cosine of theta is B parallel over B, which means the parallel component of vector B projected onto vector A can be expressed as B cos theta. Okay, the product of parallels means vector A dot vector B equals the magnitude of vector A times the magnitude of the parallel component of B, or I can write it just as A times B parallel, or ultimately the magnitude of vector A times the magnitude of vector B cos theta. That is the product of parallels, A dot B. Okay, what if I want to project vector A onto vector B instead of projecting vector B onto vector A? I'm going to draw a light blue line that's collinear with vector B so I have something to project vector A onto. Here's the component of vector A that's perpendicular to vector B. Here's the component of vector A that's parallel to vector B. I'll label this A perpendicular. Again, the component of vector A that's perpendicular to component B, and here is the component of vector A that's parallel to vector B, A parallel. That's not the number 11. Let's do the same thing. The cosine of theta is side adjacent over hypotenuse, or in this case, the cosine of theta is the projection of vector A that's parallel to vector B divided by the hypotenuse, which is just A. Or I can say A parallel equals A cosine theta. Once again, A dot B is the product of parallels, and that means vector A dotted with vector B is equal to the magnitude of the component of vector A that is parallel to vector B times the magnitude of vector B, or I could just write it as A parallel times B equals A cosine theta times B. A cosine theta, once again, is the projection of vector A onto vector B, and this can be written as A B cos theta. So once again, we have the same notation. Vector A dotted with vector B is the magnitude of vector A times the magnitude of vector B times the cosine of the angle between those two vectors. You can see that this expression on the left is exactly the same as this expression on the right. It's good to run through both those scenarios, projecting vector B onto vector A and then projecting vector A onto vector B. Okay, now let's do the dot product with unit vectors. Here's the x component of vector A, which I can label as A subscript x times the unit vector I hat. Here's the y component of vector A, which I will label A subscript y j hat. So I can express vector A as ax I hat plus ay j hat. That's the unit vector expression for vector A. Now I'll do the same thing for vector B. Here's the x component of vector B, which I will label as B subscript x I hat. Here's the y component of vector B, which I will label as B subscript y j hat. So I can similarly express vector B as bx I hat plus by j hat. This is the unit vector form of vector B. Okay, now I want to do the dot product, this time with unit vectors. Vector A dotted with vector B is going to equal vector A, except now I'm using the unit vector representation, dotted with vector B, except again I'm using the unit vector representation of vector B. So go through the process of multiplying everything out. If I do that, I get ax I hat times bx I hat plus ax I hat times by j hat plus ay j hat times bx I hat, and finally ay j hat times by j hat. Okay, I'm going to rewrite this and just group together the scalar terms and the unit vector terms like you see here. Nothing's changed, just clustering the scalars together and the unit vectors together. Okay, ax times bx is just ax bx. Those are two scalars. You just multiply them together. They're just two numbers. Let's talk about I hat dot I hat. I'm multiplying a unit vector by another unit vector, so I have to use a vector multiplication operation. In this case, that operation is the dot product. The dot product operation is always the same. I'm going to take the magnitude of one of the vectors times the magnitude of another vector times the cosine of the angle between them, just like we always do when we want to find the product of parallels. So now the question is, what's the angle between two I hat vectors? You can think that these two vectors, two I hat vectors, are perfectly parallel. This is going to result in the maximum product possible. But let's draw this purple I hat vector and then another brown I hat vector. Those are identical vectors. They're pointing in the same direction, so the angle between those two vectors is 0. Okay, so what does I hat dot I hat equals? Well, the magnitude of I hat is 1 times the magnitude of another I hat, which is also equal to 1, times the cosine of theta. Theta is 0 degrees, and the cosine of theta equals 1. So I hat dot I hat is 1, which is the maximum possible value. Let's move on to the next term, ax times by I hat dot j hat. What is I hat dot j hat? Same approach. I hat dot j hat is equal to the magnitude of I hat, which is 1, times the magnitude of j hat, which is 1, times the cosine of theta. Here's a red unit vector I hat. Here's a blue unit vector j hat. You can see they're perpendicular to each other by definition. X is perpendicular to y. Theta in this case is 90 degrees, which means there's absolutely no parallelness between unit vector I hat and unit vector j hat, which is consistent with the fact that cosine of theta means cosine of 90, which is equal to 0. So I hat dot j hat equals 0. Okay, let's continue with this third term. J hat dot I hat is equal to 0 for the same reason that I hat dot j hat is equal to 0. Those two vectors, I hat and j hat, are perfectly perpendicular, which means there's no parallelness. Cosine of theta is equal to 0 because theta equals 90. J hat dot j hat equals 1 for the same reason that I hat dot I hat equals 1. Both those vectors are parallel because theta equals 0 and cosine of 0 equals 1. Okay, so when we simplify, we see that vector A dotted with vector B equals ax bx plus ay by. Everything here has been done in 2 dimensions. What if we had a third dimension? We would add the unit vector k hat, which is the unit vector parallel to the z-axis. Unit vectors I hat, j hat, and k hat all make 90 degrees with respect to each other, as you see here. K hat dotted with k hat equals 1, but k hat dotted with I hat or j hat equals 0, so we would add an az, bz term if we use the same approach. So here are 3 ways to express the product of parallels. Vector A dotted with vector B, or ab cos theta, or ax times bx plus ay times by plus az times bz. Okay, lastly, imagine an orange bead on a wire. I want to move the bead up a wire, so I apply a force indicated by this red vector F. My force vector is making some angle theta with respect to the wire, which is my displacement vector R. My red force vector F breaks down into a parallel component, a component that's parallel to the displacement, which is the wire, and a perpendicular component, the blue vector, which is perpendicular to the displacement, again, which is the wire. As this bead moves along the wire, it's the purple F parallel force that does the work. The blue F perpendicular component does no work. It's not equal to 0, but it's not doing any work on the bead. So it's the dot product that calculates this. The work done by this applied force as it moves the bead along some displacement r is given by the force vector F dotted with the displacement vector r, which is equivalent to the magnitude of the force vector times the magnitude of the displacement displacement times the cosine of the angle between those two vectors, and is also equivalent to fx rx plus fy ry plus fz rz. This is exactly what we did with vectors a and b.